Thanks for the invitation. So there's a change in my title, but that doesn't mean that I'm not going to talk about what I promised to do. So now there are two stories, and one of them will be the thing I promised to talk about. But the reason I changed my title is because I want to talk about neural networks in the context of both natural and artificial intelligence. And that's because, this particular program is titled Mathematics of Intelligences, which is great. So this gives me a chance to talk about my work. And also, I'm motivated by these folks over here, who got the Nobel Prize a few days ago. And both of these folks were, deeply thinking about the brain while at the same time, thinking about artificial intelligence and how you would, get the foundations of how intelligence arises from neural computation in general. Now, I've been talking about this neural computation as one thing. Is there a distinction between artificial and natural neural computation? That's an interesting question. At least, to some people in the universe, they're not very different. People think, I do think that there is a sort of a way to think about neural computation, and the main sort of the question to ask here is how intelligence arises from neural networks. And of course, you could ask many questions about, can there be objections, what we think as natural neurons in the brain are not really, the kinds of mathematical objects that we deal with in a computer. If you take this sort of correspondence seriously, the network architectures that we observe in natural intelligence is very different from what we deal with in artificial neural networks. What is intelligence? What's the difference between natural intelligence and artificial intelligence? Are they the same thing or one object, and so on and so forth? This is all true, but I do feel like, there is one aspect that's common. In both types of neural networks, there is some emergence of complex computation from the collective dynamics and interactions of relatively simple computational elements. And I think it's this particular aspect that sort of could benefit from a unified mathematical, physical, whatever it is, scientific domain you're coming from, sort of study. So with that background in mind, I want to tell you just two small ideas, two stories, two ideas about, that we worked on in both those domains. And the first one is going to be talking about the mechanistic understanding of brain's algorithms. And the reason I wanted to talk about this is it's also an invitation, because this is a workshop about mathematics of deep learning, and I believe that kind of mathematics might also inform a lot about a lot of questions in neuroscience. I just want to pose a bunch of questions there and also answer something. And the second one is going to be exactly what I promised. It's about in-context learning with attention. There's not much, there's a very broad sort of commonality between these talks, but yes, let's go with it. So the first part of this talk is about the brain. And the question I want to pose is the brain mechanistically identifiable? So what do I mean by this? These are very big words. So here is the idea. So neuroscience seeks a mechanistic understanding of brain computations. Now, this word, this sentence is very loaded. What do we mean by mechanistic? What do we mean by understanding? What do we mean by computations? Even the notion of brain has been sort of, the historical sort of history behind what we mean by it. So let's focus on this mechanistic understanding, okay? A particular way neuroscientists have been addressing this is through basically dynamics. So what do I mean by this? So they ask the question, how do the dynamics of neural circuits give rise to their function? So so that arises, it's a very natural question to ask. So I'm showing you some data here. This data is coming from monkey motor cortex, where a monkey is doing an arm reach movement. Each panel here is a different neuron, and basically each different trace here, the x-axis is time, y-axis is the activity of this neuron, okay, how much they fire, and each trace here basically another trial. So the monkey is doing many, many, many reaches, and you're seeing different response profiles from these neurons. The point being here, it's basically a very highly dynamic sort of activity traces that you're seeing. And because of these kinds of things being ubiquitous everywhere in the brain, it's very natural to try to understand this from a dynamical systems point of view. And this has been pioneered by many people. I really like this particular review titled Computation Through Neural Population Dynamics. Population refers to a group of neurons and their dynamics, which articulates this sort of point of view very well. So let me just try to give you sort of a mathematical, methodological sort of version of what this means. So suppose you want to understand this kind of activity through, neural population dynamics, what you would do is something like this. You would construct a dynamical systems model of this dynamics. So a very simple and popularly used kind of model looks like this. R here is basically a vector. It's a vector whose size is the number of neurons that you are observing. It tracks the activity, let's say the firing rate of these neurons. And then there's some nonlinearity here, and there's some connectivity matrix, plus I here could be an external input to the circuitry from maybe another brain area. This is a recurrent neural network just written in continuous time. Neuroscientists and physicists like to work with continuous time. Okay, good. So the idea would be here to choose the parameters here are tau, W. Of course, this is a very simplistic view of the brain and neural networks. So you can have more detailed equations. You can add as much biological detail and biophysical detail to this as much. Each of these neurons can be described by a very complicated set of equations and so on and so forth. At the end of the day, you end up with a bunch of parameters, and you fit those parameters in a way to reproduce the data that you see. And then the question is, how do I extract mechanistic insight from a model like this? Okay? And that goes through the second process of, now I'm trying to basically summarizing common data analysis pipeline people use in neuroscience. And basically, that's just going back to the model and mathematically analyzing it. So for example, in this paper that I advertised again, they're pointing to a bunch of attractor structures that might arise from this kind of a neural network. For example, point attractors, Hopfield network, which got the Nobel Prize, is basically associating point attractors to associative memory, right? So this is an interesting idea. We're going to talk about the manifold attractors. Line attractors, for example, take part in like a short-term memory integration. We're going to talk about that a lot. Other oscillatory dynamics, ring attractors, another interesting one. So this is, again, a manifold attractor that people actually have observed in flight navigation system and so on and so forth. And all of these kinds of attractor structures have been linked to different kinds of computations, memory and sort of navigation and so on and so forth that people have thought about, hypothesized about. So that's good. So this is one way of extracting mechanistic insight from neural data. Let's go back a little bit and ask the question, how do we construct these models? In the past, we had great theorists who pondered and thought deeply and chose these W's in a way that, that could reproduce data by thinking deeply. Nowadays, we still have these people, of course, in our communities, but, in many situations, we also have access to simultaneous measurements of the activity of populations of neurons, and there's a data-driven method that people usually take. For example, so you might have a bunch of recorded neural activity. These are a bunch of neurons. These are the time traces of these neurons. So this is their activity. What you would do is you will take a recurrent neural network, and you would fit the recurrent neural network to reproduce this neural activity. What do I mean by this? You would fit every neuron in this that's one way of doing it, every neuron in this sort of RNN to produce exactly this time trace. Okay? And then what you can do is basically take your model out and then study it. It's a famous figure from a paper by Barak and Susilo here, for example, where they're trying to figure out how a recurrent neural network is trying to solve a flip-flop task using, again, these kinds of point attractor structures, some being stable, some being unstable, and so on and so forth. And there are many versions of this. Sometimes you fit the activity directly, sometimes you fit the task directly, and so on and so forth. There are many variations of this. But the point being that this is a very popular method. There are very influential papers have been written about it, and these are a bunch of papers that I like. Some names to think about. Kanaka-Rajan is a lead in this thing. Of course, Chaim Sompolinsky, people like Chaim Sompolinsky have been leading the recurrent neural networks from the beginning, and so on and so forth. David Susilo is another person we should talk about, and so on and so forth. Okay, this is all good. This is good practice. Now, the question I want to raise is the question of mechanistic identifiability, and I think this is a place where mathematics of deep learning that we're developing might help. Okay, when can we trust the mechanistic insights gained from this procedure? In other words, so let me ask the second question. Is it possible that our models fit the data perfectly, the data being neural activity traces, but get the mechanism wrong? By mechanism, I will mean the particular, let's say, dynamical structures like attractors and so on and so forth. Yeah.
So can I just ask Cengiz, is it just taken for granted that if you could just identify which kind of dynamical system you have an attractor of this kind, or you have some kind of saddle and hyperbolic dynamics or whatever, that can only have like one interpretation. That's like the end of the mechanistic interpretability. Is that like you know what I mean? Like you fit this system, you see that it has an attractor of whatever kind. I don't know what kind of attractors people care about. And that's like, if you could do that, that's all there is to gain from the system.
I mean, it's a good question. I don't know. I mean, there isn't any formal argument for this or against it, but it's certainly a practice that many people are satisfied with this kind of answer. Now, whether your personal taste is this or not, I don't know. I don't think, for example, I would be very surprised if it all turns out to be fixed points and then their linearizations, right? So I think there should be something more, but yeah.
So the second question you asked has an analog in statistics. There are settings where the maximum likelihood estimator isn't optimal because it will continue fitting noise all the way down, and then you have to regularize in some ways to actually pick out the signal, and reacting also to Boris's statement here. I mean, if we think about like say Newtonian mechanics versus quantum, right? You need a lot of data to eventually realize that you need to get away from Newtonian. See, it feels like, and that's related to the second question too, right? So it seems like we're always going to be potentially dealing with a wrong interpretation of what the mechanism ought to be, what it is, and like what it will eventually converge to.
I mean, it's great that this was obvious to you. It wasn't to me, so I did this work. So yeah, right. I mean, but I just want to point that, like, so this is a question that we should seriously ask, and I feel like it's not asked in the neuroscience community. Yeah, it's great that, like, your intuition was this. I mean, that's another reason I used identifiability is exactly to make connections to the statistical literature. You know, people in problems like, for example, independent component analysis or things like this, where you're trying to reconstruct some latent sources. I mean, this is the word that's been using. The other, I mean, maybe one little variation of it is mechanistic. So what do I mean by mechanism? It's not just like, it's a bit of there's a deeper, a bit of a different sort of vibe to it. I'm not going to talk about statistics per se, but I'm going to talk about whatever people think are mechanisms. Okay, cool. And of course, there are many possible issues here. Neural circuits are partially observed, meaning whenever you're recording, you record only a bunch of these neurons. There are many cases, I mean, sometimes, neural activity is noisy, okay? So, and in a lot of cases, especially in natural settings, nothing is ever repeated, so you just get one sample. On top, measurements are noisy, biased, low in resolution. And of course, this is also a big one. There's a mismatch between brain circuits and the mathematical models. I mean, the particular equation that I wrote is a huge simplification of what might be happening in the brain. So given all of this, you might ask, what can we hope to recover? Right? So, for example, it might be that you recover somehow the connections, the weights, right? I mean, so that might be good if you did. That's good. And then, people have pointed that, I mean, that's not going to happen. There is some, systematic biases and, data constraints that will just give you the wrong weights. Perhaps a more modest goal is capturing the mechanistic dynamical properties. So this is the things I was talking about. Maybe you want to recapitulate slow time scales, unstable directions in neural space, oscillatory dynamics, attractors, so on and so forth, right? So maybe these are the things that you can recover. Okay, cool. So this is the general question that I want to pose as a bigger research program. What are the limits here? And for this remaining, I don't know, 20 minutes or something, I'm going to talk about a setting where basically everything else is okay. So I'm going to assume a setting where basically none of this is an issue, and only there's just some partial observability, and see what can go wrong. Okay? And this is going to be a work that's going to appear in EURIPS with the title Partial Observation Can Induce Mechanistic Mismatches in the Data Constraint Models of Neural Dynamics. And what I'll do is basically give you an example of where this will fail. Okay? And for that example is going to be be motivated by this temporal integration of scalar inputs. So I'm showing two kinds of experimental results, up and bottom. So what's happening here? These are two different settings. This relates to the oculomotor system. So when your eyes are moving, right? So there's an angular sort of position of your eye. So so this is coming from goldfish, but okay, I talk about you, but so this is basically what happens to the eye. This is a particular recording from a neuron in the brainstem. Okay, so what you see is basically this neuron is bursting whenever there is sort of a rapid movement in the eye's position. So this is like a velocity neuron. And in the same circuit, there are other neurons which behave like this, which are basically integrating this velocity input. For example, you can track the eye position across time, and this neuron's overall firing rate will basically track this. So this is so people think that these neurons are integrating the velocity input. They are temporal integrators of scalar velocity signals. This is another experiment. This is from prefrontal. These recordings are from prefrontal cortex. The task here is the following. This is a monkey getting some tactile stimulus. So the idea is the following. The stimulus has a particular frequency. The monkey sort of senses it, then waits for a while. And there's another stimulus with a certain different frequency. And depending on if frequency 1 was greater than frequency 2 or otherwise, the monkey has to do something. I don't know, read something, staccato something, and so on and so forth. Okay? So here you're seeing one neuron. This is the same neuron across different sort of conditions. So each color corresponds to a different frequency of the first stimulus. And during the period where the first stimulus was presented, it's this line over here, you see that basically its activity ramps. And how much it ramps is basically a function of the frequency itself. And so there's some kind of integration happening again, and then persistence, and so on and so forth. Okay, so this is I could give other examples like this. So there are many neurons that, other areas that people have seen this kind of persistent activity where neurons integrate scalar inputs and remember them. All right, so let's try, and obviously, many people try to model this, okay? So let's think about now a recurrent neural network, okay? So this is going to be my neural network. There will be an input signal. I just made up some random time series here. And the idea is basically I want to have a readout neuron here, which is going to sort of temporally integrate what the input is, okay? And then, and how would you construct the circuit? There are many ways to construct them. Many people have come up with different ideas. So what I want to do is compare and contrast two different ways of doing this. It's interesting that, if you follow the literature on state space models, a lot of these ideas came back. It's basically boils down to these earlier ideas. I don't think people have realized the connection, but it's just the same ideas. Okay, so here is one way. So this is by using a so-called line attractor. So here's the idea. So what you do is, so think of the weight matrix here, and let's think of basically an eigenvalue decomposition. Okay, so this basically diagonalizes the modes of activity. I'm going to deal with linear networks for simplicity here into different modes. And suppose one of these modes have basically an eigenvalue exactly 1 or very close to 1, and everybody else is just 0, right? So what that means is activity that's coming to this mode or projected to this particular mode input gets integrated over time. That's exactly what it does. And then you can just directly read out by projecting the total activity to this particular mode, and that will be a temporal integrator. Now, there's a second way of doing the same thing through a feed-forward mechanism. So here, the right way of diagonalizing is through Schur decomposition. So basically, again, you have a bunch of orthogonal modes, but they basically have connections or propagate activity from mode to mode to mode to mode. So you give an input. This activity goes from one activity mode to another one, and to another one, to another one, and so on and so forth. It reverberates in the network for however many steps that you have. And then you would read, the way you would integrate this is basically, again, adding all of these guys, which are all of these particular projections that are available in the circuit with the correct weights. And then you can reconstruct the integrated signal. Okay, so this was very quick, but I'm sure you can work this out yourself as well as a simple idea. The story being which, I can construct this circuit in either way. So through a line attractor or through a feed-forward chain, and I will basically get a perfect integrator. Okay, now now let's do the experiment in silico that we do in neuroscience. All right, suppose, now we take one of these neural networks and partially observe them, let's say 5% of it, okay? And then fit a neural network to this 5% observation. The question is, will it recover the original mechanism? Will it give me a feed-forward chain or a line attractor? Okay? So this is basically the mechanistic identifiability question. answer, I mean, first, you can do the fits, and you can get basically, learned activity match exactly the ground truth activity that you're going to get. And these are, these can be predictive even for some time scales and so on and so forth. But, okay, let's look at the mechanism with which they do the thing. So this is the phase space of the activity in the first, like a line attractor. This is the ground truth. Here, as you see, the activity first goes to velocity fields, goes to the attractor where there is no velocity, and then you do your integration on that attractor sort of dimension. And in the feed-forward chain, the activity goes, is not basically following there is no, first of all, space with zero velocity field, and the activity is going up and down somewhere here. But if you look at the learned models, so these are the trained models, in both of these cases, they will end up solving the problem with a line attractor. They will end up basically learning a slow dimension. Okay? So if you were to just look at the learned cases and study this, and make mechanistic inferences about ground truth, here you will be okay, but here you will make a mistake. You would assume that there was a particular attractor structure which didn't exist. Okay? All right. Okay, so let me give you a little bit of intuition to why might this happen. So it's actually a very simple intuition. So let's literally think that neurons were organized in a chain-like fashion, and there was an input going from some kind of a pulse going from one end, and it was propagating from this neuron to this neuron to this neuron to this neuron to this neuron in time. Okay. All right. So, and we put our electrodes into the brain of this in this brain and caught a bunch of neurons. For example, we end up recording this guy and that guy. Okay. Now we have a model that has to reproduce activity of this guy from this input, but there is a sort of a long time frame here that I have no neuron to put the activity of, right? So I have to have this neuron wait for a while and then jump and so on and so forth. And you can convince yourself that the only way it would actually it would do this is basically through introducing a self-interaction, which is going to basically like reverberate activity here and then suddenly make a little jump when the time comes. So this is basically like introducing an extra eigenvalue to the problem. And so in neuroscience parlor, this will be called OTAPS. OTAPS meaning synapse is a connection you make to another neuron. OTAPS is a connection that you make to yourself. Okay, so we can actually mathematically prove this as well, but basically I'm not going to go just informally tell you that. So suppose there was a teacher sort of linear network and a student which is lower dimensional, and you do some partial observation for some time. If the teacher connectivity matrix is a normal matrix, which is like attractor-like in this case, then you're good, meaning recovered eigenspectra are quantitatively similar to ground truth. You can put some epsilons and deltas into this. This is good news because a perfect line attractor happens when one of the eigenvectors is exactly 1 and the others are small. Okay? But when you have a non-normal matrix, B, so that's more like feed-forward-like, then things get complicated. I show you one example where things broke down. You can even get like, manifold-like attractors where there was none in the original case. So here's one fun part. So all of this was about linear neural networks. So I don't have any theory for this, but this is a beautiful one example. In the first slide, I showed you these oscillator-like dynamics. Okay, so you can have basically, and the other thing I told you is like a failure mode is basically overestimating the eigenvalue. Suppose your neural network generates oscillatory dynamics through some kind of a stable spiral at some point, but the relative eigenvalue is very close to the stability line. Okay, so your student might overestimate this particular eigenvalue and become unstable. So now you have an unstable spiral that's coming out of the origin. Let's say that's where the thing is. Okay, but still your fit has to work, right? Because you need to generate an activity that's not going to infinity. So what you do is you end up introducing a limit cycle to the problem that didn't exist. So this is exactly what's happening here. So this is the original phase space of a ground truth neural network. The neural activity is basically going through a fixed spiral over here. The trained network basically overestimates this eigenvalue, or underestimates, I'm not sure. Basically, it gets a bigger eigenvalue, so this becomes unstable. Somehow you have to spiral out. However, the point is you still want to get like your fit has to work, so you need to get like stable activity, so you introduce a limit cycle. So, I mean, I mean, this is relevant because, again, this kind of rotational dynamics people have been talking about a lot in neuroscience. So again, whenever you see a limit cycle in your data, this may not be what's happening in hindsight.
Can I ask, Cengiz?
Yeah.
So just to kind of contextualize this, so is part of the problem that there's this complicated network and you're not observing enough of it to understand the connectivity in the network, and that somehow maybe 5% would be enough if you chose the right 5% of neurons or something?
Yeah, so that's a good question. So what is the right, so for example, is there a magical number I can give you, let's say 60%, and you'll be fine? So there isn't, it turns out. I mean, it really depends on the problem and which 5% or which subset that you get. Okay, so we're trying to analyze this basically in some idealistic settings, and then what you're seeing is a crossover kind of a transition. So basically, so you can come up with metrics that tells you how well of a, let's say, feed-forward structure you capture. It doesn't go from 0 to 1, but it's basically, let's say, it goes like smoothly from 0 to 1. So I mean, so it's a good question. So what do I do with this fact? Okay. So one thing that we are thinking about moving on this is basically giving a practitioner sort of some validation tools. So for example, I give you data, you fit, and then you should be able to validate your model. I'm saying just prediction on some time frame is not enough. We should have other validation tools in the absence of ground truth. It turns out, for example, if you don't look at spectra of your model, but pseudospectra of your model, for the kinds of things that have mismatch, you do see basically lots of signatures there that can tell you that your model was not doing well. Okay, so just want to conclude this part. Partial observation can induce mechanistic mismatches in data constraint models of neural dynamics. But this was again our small contribution. But I think the bigger question here is this: how do we extract Bayes' algorithms from neural data? And I do believe that again, a lot of methods that I also work on this field, that we're thinking about neural networks, how do they learn, supervised learning, and all that kind of stuff, can be helpful in sort of asking these mechanistic kind of questions about neural data. So any questions about this before I move on to my second part?
So, I mean, is another way to look at this that you have high-dimensional space and you're projecting to a lower-dimensional space.
Yeah.
You have a vector field, a dynamical system upstairs. Downstairs, you have some curve up here, a curve down here, but each point, the pre-images have different vectors that project to different things. And so that's, of necessity, going to mess you up. And in some sense, what you're saying is even if this is sort of a linearly defined vector field, you still more or less can't recover it.
I mean, certainly you're making a great point. In these particular examples, even if you were dealing with a high-dimensional space, the underlying dynamics was inherently low-dimensional. And so your point is absolutely correct. In this particular use case that I've described, the low-dimensional system could actually solve the problem, could recover. There is a solution that could give you the correct line attractor. It's just that the data analysis method has a bias towards not finding that solution, but finding another solution. But yeah, certainly that's another point you're making. Yeah, exactly. That is true. Very good. Okay, excellent. So, and then from here, I want to move on to a total different problem here, but it will have this mechanistic aspect in it too. And this is again a talk. Now, I'm going to switch to talking about so-called in-context learning, and this is a problem that people have been talking about in machine learning a lot. So the idea here is basically the following. This is the ability. So in-context learning is the ability to learn and execute tasks based only on examples seen in input, without needing explicit training. So this is an ability of a model, okay? So this is an interesting example. So let's think of basically ChatGPT. This is exactly what you're writing on the prompt, okay? So this is the examples that you give. So for example, this is exactly what you write. You say input 2014-0601, output this, input this, output this, input this, output this. So there's obviously basically a sort of a rule here, right? Basically, you're supposed to take the month first, the day second, and put exclamation marks, and so on and so forth. And then you give an input, output, maybe you might give a question mark or something. The model is supposed to basically figure out, from these examples what the rule is and output the correct solution. Okay? So sometimes this in-context learning is compared to so-called in-weight learning, the idea being that you have to update weights to learn a task. Okay, here the weights are fixed. This is just you're defining the task as you're writing on the prompt. And this is an interesting ability. People have said things about this being a fundamental ability of LLMs for whatever their success and so on and so forth. And of course, just looking at this, there are a bunch of questions that one might ask. For example, how do the different algorithmic and hyperparameter choices that go into training our models affect this kind of performance? How do transformers actually solve in-context learning? There are also questions about sample complexity, how large a training set you need for this to emerge, context length, how many examples should you be giving so that this machine can actually understand the rule, and a task sample complexity. So this is a bit of a notion. So presumably for the transformers or language models to be able to understand that there's a task to be solved or learned, in their training, they have to be exposed to many, many, many different tasks somehow. And from there, they'll be able to come up with some generalization here. So can we ask about this? How diverse should the tasks in the training data set be for in-context learning of truly new tasks not encountered in the training set? It's a good question, and many people in the field are trying to answer them. And so the path we'll take here today is basically addressing that in an exactly solvable model. And this is in-context learning for linear regression by linear attention. So I'll introduce these things, but any questions about what do I mean by in-context learning? Yeah.
Yeah, question. From the philosophically, what's the difference between the example you showed and supervised learning? Is it because the weights of the model are frozen and there is no learning to get, what's the difference between that and supervised learning?
Yeah, it's a good question. In 2 slides, this is something I ask myself. So in 2 slides, I'll try to formalize it in a way, and then we can discuss if you agree to it or not. Okay, yeah. Okay, cool. And this is a problem that has been studied by many, many people. We're not the first to do this. In particular, I want to highlight this paper, Alan Raventos's paper, Surya, that has motivated. It was an empirical paper with a lot of interesting observations that has motivated what I'm going to talk about. I saw his poster out. I'm not sure if he's around, but if he's around, you can ask him about this paper. And in particular, we're going to talk about, so the difference of what I'm going to talk about is basically sort of an asymptotic analysis of this particular model that basically nails down all these questions in a very precise way. Okay, and this is a collaboration with my students and Yue Lu, who is an expert in all random matrix theory kind of stuff, and we'll see his contributions. Okay, good. All right, so let me try to sort of formalize my way of thinking about this. So the goal is like this. So we're going to be given basically a sequence of sort of tokens. So I'll sometimes call this context, okay? So basically, you'll be giving up pairs of some x's and y's, so L of them. So these are basically, the context. And then you'll be given a token, which is a query, xl plus 1. And the goal of this machine is to predict the corresponding yl plus 1. So that's what you're going to put in to the model. And the model is supposed to predict yl plus 1. So let's try to formalize this in a sort of a Bayesian kind of a setting, okay? So let's suppose there's a collection of joint probability distributions on x cross y. Okay, so basically this, so the relation between x and y can change context to context. Okay, so that rule I'll formalize by a collection of joint probability distributions. Okay, so for each input sequence, first we're going to choose a joint distribution from a distribution over these distributions. I'm talking loosely here. And I'm going to generate the sequence with x and y pairs sampled from this distribution. Okay? So what the model has to figure out is basically, what this mu xy was, and depending on that, give basically a solution. Now you could think of this as a super meta supervised learning problem. It's also fine. But, okay. So this is how I'm going to think about this. And of course, the key idea here is that during pre-training, the model has to learn this prior distribution on joint distributions, right? So that's the idea, so it can make the inference well. Okay, so let's try to, okay, so this is, again, a very general problem. So let's try to do this like kind of analysis for the simplest model. So this is an ICL of linear regression tasks. So what do I mean by this? Again, the input context is a bunch of XY pairs. I want to predict what happens when I give XL plus 1. Okay, so the relation between X and Y is going to be given by a linear model. So for example, every Y here will be X dotted into a W, which I'll call a task vector. All these vectors will be d-dimensional vectors, and maybe add some noise, and that's what you give to the model. Okay? The point is this W is the same W across all these examples. Okay, but I don't give the W to the model. It has to just learn what this relationship between these pairs of points and make a prediction. It's basically, it has to solve a linear regression task. Okay? So we can make some assumptions here. For example, to make our life easier for analysis, I might assume my x's are coming from some Gaussian with basically identity covariance. There's some noise. The noise has a variance rho. And importantly, the task vector for each sequence will be a different thing. Right? So every time I'm putting this, the W will be a different W, so the model has to figure it out in context. Again, this setting is very similar to these Fox's settings, so we're just following them. Okay, so this is what happens at test time. I give this to the machine, and the machine has to figure this out. All right, so how do I train the machine to solve this? So again, this is where we're going to create a data set, okay? So the idea of creating this data set is we have to give it some idea of possible tasks, okay? So we'll be having the data set will consist of n such sequences, all right? So now I introduce a mu index, mu goes from 1 to n, all right? And basically for each of these sequences, I generate data exactly the same way, but there's another notion here I introduced. So this is a task diversity idea. So I will be having a task vector set. So these W's will not be anything, but I'll choose them to be one of k things. For example, if k was equal to 1, during training, the model will always see the same linear relationship. So you would intuitively expect that it won't do ICL because, you know, it has only seen one W. It will probably always try to fit data with the same W. So we want to understand basically how much diversity that you need for this model to be able to generalize beyond this task and really rely on the examples that you have given to solve this, okay? So basically, the way we're going to train this or generate this task is, or data set is, for the muth sequence, sample the task vector W mu uniformly at random from this set. Let me stop here, and if you have questions, let's take this.
I think that n is being much larger than k, right?
N is being much larger than k. Okay, so that's a great question. So the scaling of n, k, d, there's a bunch of things. That's exactly the question I want to answer. How large should n be compared to k, and context length, and so on and so forth? And I'll have an answer for you. Excellent.
So which model are you testing?
Testing?
Which model are you testing all of this on?
Okay, so I haven't told you the attention model yet. That's my next one. Okay, so I will train what model? Okay, so that will be a linear attention model. What do I mean by linear attention? Okay, first let me talk about embedding. Let me just talk about all of them at once. All right, so I'm looking for something I can solve. I'm going to basically tokenize, embed all this data in a matrix Z, where x's and y's come in pairs, corresponding y's. This choice seems to make a difference. I mean, you could tokenize in different ways. This makes analytics easier. So this will be a D plus 1 times L plus 1 matrix. And I'll put a 0 here. 0 basically is for prompting the model to produce or guess that empty, or that particular element. And the model, the machine learning model that I will train to solve this task is given by this. This is linear attention. I mean, linearity here, okay, so this is actually nonlinear in data, so Z cubed, as you see, okay? And then the idea is we remove the softmax. There's no softmax here. And K, Q, V are value, key, and query matrices of a typical attention layer. And there's also a skip connection, and so on and so forth. Okay, and for prediction, again, this machine takes in a Z matrix and produces an output that has the same dimension. So we're going to look at this particular element of the output of A to basically make the prediction. Right? So this is the model we're going to study. Okay, so the question is now, how can this kind of a machine solve the task that I described to you? Okay, so we can do a bit of linear algebra here, and just algebra. Okay, all right. So just to make my life easier, what I'm going to do is basically rewrite these parameters. This is the value matrix, and keys and queries, I'll combine them into one M matrix. These V's and M's are D by D matrices, and small m's are basically column vectors, or basically M22 is a scalar and V22 is a scalar. So after a bunch of algebra, you can write down the predictor, the prediction that this machine makes in terms of this equation. It boils down to basically just a linear predictor, okay? I should say that I had to omit or assume that some parameters are 0 here, very few of them, and that there's arguments coming from symmetry and optimization that says this is okay. And I'll show you simulations that this works. But just by looking at this equation, you can see what's happening. Okay, so let's see what's happening. So this gamma is a matrix that combines all the parameters of this attention module. So it's basically a function of the parameters. And H is basically all the data that you give in context. It's just like, combined into different forms here for processing. So let's look at what's happening here. So this is the term that's important. So you're seeing, so I is basically the index within one context. This is a correlation between X and Y, okay? So remember, Y is W dot X, right? So if, L was about size D or more, you'll get an XX transpose, and this is basically going to estimate the covariance matrix, right? So this is going to be basically covariance times W. The covariance times W multiplied by XL plus 1 is going to give you covariance times the correct Y. So that means that if I were to sort of learn here in M11, the inverse of the covariance of inputs, I should be able to solve this task.
So can I ask, so is this dependent on the loss you're going to use this form? Or is just because it's linear, this is all you can use?
I didn't talk about loss. This is just the functional form of the predictor.
So it just comes from the linearity of the attention.
Exactly. So I just plugged in, I just looked at this equation. I just looked at this equation and plugged in. I didn't tell you how I trained this, okay? But this basically tells me about tells me a lot about the complexity of things that I need to have, right? So this sum should be able to estimate the covariance of X. So what that means is basically, suppose I was taking D large, this was high dimensional vectors, the context length should scale linearly with it. Otherwise, if it didn't, it will either be a too hard a problem or a too simple a problem, right? That's like the random matrix theory regime. The number of examples, well, I'm fitting about D squared parameters. So it sounds like the number of examples, pre-training examples I need should go like D squared. Task complexity is more interesting, so we're going to talk about that.
So and these brackets are like trace?
Yeah, so this is a trace. Sorry, this is a trace between those two matrices. Cool. All right, so now let's talk about training. So again, we can do a training loss by, so I introduced a training procedure, but I'm going to do this using like a ridge regression now, okay? And obviously this is this is nice because now everything is a linear prediction and so on and so forth. There's a solution for optimal gamma here, which is going to be given by sort of a standard ridge regression formula, right? The difference, if you're used to analysis of linear regression and so on and so forth, it looks very similar. The difference is now these are vectorized random vectors whose covariance is much more complicated than just IID Gaussian. So you have to introduce a bunch of, so it's a random matrix involving tensor random vectors, and you have to use some random matrix theory to analyze this algorithm. And this is exactly the point I was stuck for a while. Then I met Yue, who magically knew the exact trick, and we were able to make progress and solve this problem. Okay, good. So what we're going to do with this, so we're going to calculate generalization errors. Okay, so what do I mean by this? I'm going to plug in here the optimal gamma and make predictions on new test data and basically calculate this over all possible choices of W's, X's, and epsilons. But I'm going to make a distinction between two different kinds of test distributions. In one case, during the test time, the W's will be sampled from IID from a Gaussian distribution. Remember, in the training data, my W's were confined to being one of K guys. Now, I really want to test in-context learning, meaning the model's ability to make predictions on W that it hasn't seen. So I'll average over sort of W's that's coming from any sort of W. And then I will do a second version where I'll call this in-distribution generalization. But also at test time, I will give it to basically one of the K guys that it has seen in training time. Right? So this is sort of like in-distribution generalization. It's trying to solve the task it's in training time. This is sort of like testing what happens in context learning. And I should mention that this is, again, like a setup coming from, this particular setup is coming from the Reventus paper.
Can I ask you this? So just to connect to Elvis's talk from yesterday, this difference in like in distribution and in context. Can you just think of it as like there's one extra term in the bias variance decomposition that kind of comes from how representative your W1 up to WK are of like all the possible W's you could have gotten? Is that kind of the difference in the generalization, or is there just more to it given the way that the problem?
I mean, it's a good one. We have asymptotic formulas. We haven't analyzed them in the way you're describing. I wasn't here yesterday, but I missed the talk apparently. Could be, I don't know, but there are equations. It sounds plausible.
It's like vaguely reminiscent. It's like you have a full distribution of W's and somehow truncate it by only having a finite number of observations that you use for your training.
Yeah, exactly. And this intuition this particular intuition that you have will explain some of the things that I'm going to show, so it might make sense. Okay, cool. All right, so this is great. So now coming back to your question, so now we have to make choices about so we're going to analyze this. We want to take things to infinity so that we can solve this problem. So we have to think about how things scale, right? So given dimension of data, how much a context length should I have, and so on and so forth. So let's look at the parameters of this problem. So D is token dimension, so the dimension of this X that goes into this problem. L is context length, how many examples I'm giving you within one context. N is the number of context sequences in the pre-training data set, so my sample complexity is here. And K is task diversity, number of unique task vectors in pre-training. All right, so after long thoughts and so on and so forth with my colleagues, we've come to the conclusion that this is the right way to scale things. All right, so all of these are going to go to infinity such that the following ratios will be order 1. So let's think about everything as we're scaling token dimension. Context length will scale linearly with token dimension. Okay, this is coming from the fact that we have to estimate covariances along the way. So this one is basically a sample context complexity. This is going to scale quadratically with dimension. So this is coming from that trace gamma m, and the trace has n squared elements. Sorry, d squared elements. And this is a bit non-trivial. The task diversity, number of unique task vectors in pre-training, it turns out has to also go with d in this case, d being the number of input dimensions. So given all of this, we can now answer these questions: sample complexity, context length, and task sample complexity. So I'll just tell you there's a result. The result is basically we can, in the limit of these things going to infinity, we can sort of analyze these objects, and they go to sort of, they concentrate, and they become sort of deterministic objects, and we can write some formulas for them, exact formulas, in terms of these quantities, or rather their ratios, plus the noise. So this is what it is. What I'll try to do is basically give you some simulation results and basically make a connection to the previous results. So you can look at these equations and try to see what they show. So here's one thing they show. For example, you get a sample-wise double descent in this kind of a setting. So on the y-axis so we have the same thing for both in-context and in-distribution test error, and both of them show the same phenomenology. So I'll just plot ICL. So what you're seeing is basically both in the ridge and ridgeless cases, as the ICL performance, as the number of samples approaches d squared, basically picks up a overfitting peak. Okay, so this is very reminiscent of typical things. A surprising finding is basically dependence on context length is non-monotonic, meaning that longer contexts are not necessarily better. So it's an interesting observation. I don't really have intuition for this, but there's a phase plane here. So this is a phase plane in terms of noise, and kappa being the task complexity. So if you're here, more context length is better, and here there's actually an optimal context length. So you can show these you can see these in these curves, X-axis is context length, Y-axis is ICL performance. And the final thing I want to do is basically compare, just to compare, yeah, sure.
Just like a quick question about this plot. So was the model also trained with a fixed context length? Sorry, I missed it.
The model is,
Not the context, but I mean like,
so alpha, yeah, the model and at test and train match each other, so that's what it means. Yeah.
Okay.
So, okay, that's it. I mean, context shifts are so interesting. It turns out it's not, well, we can talk about that later. Okay, so last thing I want to do is basically compare the model's performance to Bayesian benchmarks. And so what do I mean by this? Suppose I just didn't tell you about anything. I just give you a bunch of data like this, right? And you were trying to do ridge regression, right? So a very reasonable thing to do is basically, you're supposed to solve, this problem. A very reasonable to do is just ridge regression, right? So this is like a Bayesian estimator with the prior being doubly sampled from Gaussian isotropic prior, which is the right prior in the test case. Okay, and then we could also compare to another sort of estimator where the prior is that the data is, the W's are coming from the W's that I have seen in the training set. Right, so here, my prior is W's fresh sample from isotropic Gaussian. Here, it's basically one of the things I've seen in the training set. Okay, so the two different estimators. Now, and this is the paper I've been talking about, this Alan Reventis' paper. They exactly did this experiment and compared the prediction of the, in this case, they were looking at more realistic architectures of transformers, and we're comparing it to these two estimators. So x-axis is their version of pre-training tasks, task diversity. Y-axis is basically estimation performance. The green line is the predictor that assumes that W is one of the 5 things or K things that you've seen. So that's the performance. And the blue one is basically the ridge estimator. And the behavior of the transformer architecture for small tasks acts as if like it was doing a DMMSE estimation, and later on transfers to being like a ridge estimator. So you can think of this as like a memorization to generalization and kind of transition. Here I'm memorizing the K tasks I've seen in the data set, and here I'm generalizing to NW. Okay?
What's here?
So K being the number of different tasks that was available in my training data set. This is a plot from somebody else, and this x-axis is exactly their version.
Oh, so all W's in those tasks are different.
Yeah. So in my training task, in my training set, I commit to KWs, and I always choose one of those Ks. So that was my setting from the beginning. I can explain to you later because it was a K.
So you had N and you had K. So you had the number of tasks.
So N can be different than K, exactly. So
yes.
for each of exactly. So this is K.
Okay. So what is N then?
In this particular experiments?
Yes.
I mean, they chose an N such that these models behave well. So this is a bunch of experiments that I'm showing from other people. I'll show you my version of this now. Okay. So in our hands, basically, you can get the same thing. And basically, okay, so this is the same plots. This is the MMSE estimator. This is the ridge estimator. Kappa is K over D. So N is the tau is N over D. In the limit that tau is going to infinity and alpha goes to infinity, you can show that there's a sharp phase transition actually. Beyond for kappa less than 1, I mean, you're somewhere between MMSE and ridge, and above kappa greater than 1, you're exactly on ridge. So this is exactly the scale where this happens. So you can actually get this from this theory. All right, so this is the final slide. I know I'm out of time. So we've tested some of these predictions on nonlinear transformers and multilayer transformers. Obviously, we cannot draw theory curves, but we can at least test our scaling relations, right? And so this one is basically showing, for example, so we train them in an offline setting. We get the double descent, and we're plotting the double descent sort of peak and how it scales with the dimensions of the input, and we get the correct scaling relationship that basically trained, that basically we predicted from linear models and so on and so forth. Anyway, so I want to finish this by thanking my collaborators and my co-authors, and happy to take questions. Thank you.